Hi folks, I'm Paul and welcome back to my channel. Thanks for dropping by. Today in the continuing series of my Super 7 build here, I want to go over some of the brake theory, how I chose the master cylinders that I did, and it's helpful I think and interesting just to look at how sort of the theory of the brake system and maximum pressures, all that kind of thing. So we'll be going through some of that. As has been said before many times, it's not the brakes that stop the car, it's the contact patch between the tire and the road. That's what limits how fast a car can stop. It's all related to to that friction point there, and that's what determines everything. So that's what I based my calculations on, and my just the whole system. Of course, as brakes, just quickly, the way they work, there's the rotor, which is attached to the to the wheel, obviously through these lug nuts, and there's a piston in here which is driven by fluid to clamp the brake pads against a disc, and this friction stops this from turning, and then that of course is transferred to the wheel, which stops the wheel from turning. So those that's the sort of the train that has to happen for the car to stop, and that's what we'll be examining a little bit more closely. All right, folks. We're going to get into a little math here, but don't shut me down yet. It's going to be pretty simple math, and and you get into any kind of serious engineering, you have to do a little bit of math. So remember, math is your friend. So here's a rough sketch of a wheel and brake system, the tire and the road, and the brake disc on the inside here, a rotor, and there's the caliper there. So this contact patch here is the limiting factor for how well it'll brake, how much braking force you can put in, and that of course is generated by the piston pushing on the pads, which clamps on the rotor and stops it down. So this contact patch here is one of the determining factors. The friction force there is determined by two things. One, the tire and the quality of the tire and everything generates a certain coefficient of friction there, and the other is how much weight is pushing down, the force of pushing down on that contact patch there. Here you see a sketch of the car. Front tire, back tire. Under heavy braking, a rule of thumb is that the 2/3 of the weight is going to be on the front wheels and 1/3 on the back wheels. So that's, say, a 66% here and 33% there. That, of course, is determined by a lot of things. One, by how high the center of gravity is in the car. The higher the car is, the more weight will transfer to the front. It'll be determined by how well it's stopping. So if you put better tires on, it can stop better, so more weight will transfer. If it's the condition of the road determines that too. If it's on wet pavement, you get way less braking force, so there'll be less weight transfer. But for dry roads and regular tires, this is a good rule of thumb to work with, and that's what I'm going to be working with for this for what we're doing here. Another thing that determines how much mass, of course, or weight is pushing down is the weight of the vehicle. Obviously, I don't know what exactly this is going to weigh. A lot of these cars weigh in the area of 1,400 pounds. So they're pretty light, and so that's what I'm going to use for these calculations. You have to make some assumptions and go from there. And of course, you can refine these figures later, but just for something to work with, we'll go with that. Okay, so let's work everything based on the point that this is going to start sliding. That is determined by, as I said, the weight pushing down on it and the friction force here, or the friction coefficient. You can look up tables for everything sliding on anything else. The friction coefficient for a decent tire on asphalt is about 0.7, something like that. It's a friction coefficient. 0.7 is the friction coefficient. And then of course, how much weight is pushing down here is from here, 1,400 pounds total. So 700 pounds on each side of the car. So that means on this tire, there's going to be 700 times 66%, which equals, what was that again? 470 pounds. So 470 pounds on each of the front tires pushing down. Okay, so the total friction force there that's available until that tire starts sliding is 0.7 times 470. So 470 times 0.7 equals 330 pounds. That's how much force this can generate before it actually starts sliding on the ground. Okay, so if we can only put in a maximum of 330 pounds of force, of braking force in this, we have to figure out what our torque, or our brake torque is to determine what our pressure here can be, or what our force has to be in the coming out of the rotor. So if the torque is this force times this distance, has to equal the same as the braking force on the rotor times the distance from the center to the to the middle of the pad here. So on my car, this distance is 280 millimeters, and this distance is almost exactly 100 millimeters average. So 330 then. Let's do this here. So 330 times 280 has to equal the braking force on that wheel. We'll call that F times 100. So if we calculate this out, what does it work out to? So this times this divided by this. So the friction force in the disc has to be 924 pounds. So that's the force that's stopping this from turning. It's not a pressure, it's just a force that's stopping it from turning. And since there's pads on both sides of the disc, we have to divide that by 2. So 924 divided by 2 equals 462 pounds on each side of the caliper. I'm running out of space here, so I'm just going to erase this and go back to the top here. So we need to generate 462 pounds of braking force, of force that stops this from turning on each side of this of the brake disc. Like the wheel on the road, you can look up what the coefficient is for a brake pad pushing on cast iron, and that number is about 0.4. You can get higher or lower depending on if you get racing pads. They'll be higher, but 0.4 is a pretty good number for an average pad. So 462 divided by 0.4 equals 1,155 pounds of pressure pushing the pad onto the rotor. Now that is divided up over the piston, right? The piston is pushing into the pads, so that's what generates that force, and that is then over that area of the piston. Those pistons in the front of a Miata, and the ones that I'm using, are 2-inch diameter pistons. So area equals pi r squared. So let's go diameter. It's easier to do here. D squared over 4, which equals pi times 2 squared over 4. 2 squared is 4, and 4 cancel. So the area then of the piston here is 3.14 inches squared. So this force has to be generated by this area. So then this divided by this, it will give us the pounds per square inch that has to be driving that piston. So it's 1155 over 3.14. About 300 equals about 300, let's call it 370 psi. So 370 pounds per square inch on that caliper will stop that wheel at when you're braking. So that's the sort of the maximum psi we can put on that with those tires and those conditions. Okay, so we've determined that 370 psi on these front calipers is going to start to lock those wheels up. Now we can do the same calculations on the back. Everything's the same. All the numbers are the same except for 2 of them, I believe. One is the weight that's going to be down here, so that force instead of what was this 370 or something. Excuse me. That was this was 470 pounds here, pushing down. And then this one here is going to be 230 pounds. So that's that number is different. The other number that's different is the area of the pistons. The Mazda put quite a bit smaller pistons in it because you don't need as much braking force in the back. So these pistons are 1.25 inches, 1.25 inches. So those are the only 2 numbers that are different. All the rest of the calculations are exactly the same. And you go through it, and you get to 472 psi on the back calipers will start to lock up that wheel as well. So 472 psi. So having calculated these 2 numbers, we have to decide what size master cylinders we're going to come up with, and if it's reasonable. One of the basic elements of selecting a braking system, and one of the things you want to achieve, is that the front wheels always lock up before the back wheels, because that front wheels locking up is a stable condition. But if the back wheels lock up first, the car tends to flip, it tries to change ends on you. So what this means in this application is that I want to reduce the pressure on here. That if I have 370 in the fronts, I don't want to have 472 or more than that in the back. So I'd like to reduce this by maybe 10%, which takes 50, so maybe 420 psi maximum that I want in the backs if I have 370 in the front. So that means that the fronts will be locking up, the backs will still be turning. So given that we are at 420 psi here, that's what we want in 370 there. We're close enough that I picked the same master cylinder sizes. I picked 7/8 master cylinders, so 0.875 inches diameter for the master cylinders. Okay, so now we have that. Let's look at what the brake pressure, like the pedal pressure, if we have the master cylinders here, 2 of them, and there's a brake pedal there pushing on those ones. how much pressure has to be put on that to generate these kind of pressures. So if you have 0.875 diameter master cylinders, the area of them equals pi d squared over 4. So we'll work that through 0.875 squared times pi divided by 4. You end up with the master cylinder being 0.61 inches squared. And since in that master cylinder arrangement, there's two of them. There's there's one that goes to the front, one that goes to the rear. The total area there of those master cylinders is that times 2, or 1.22 inches squared total. So if we need to generate, say, an average of, say, around 400 psi, just for calculations, and we have 1.22 square inches to do it with. We have 1.22 times 400 is about 400 equals 488, or say 500 pounds of pressure. Now that's what the pressure. That's the force that we have to generate right there into the master cylinders. But we have a lever arm here because we're pushing with my foot there, and here's a pivot and here's a pivot. So these pedals are a 5.25 to 1 ratio. So say 5 to 1. So if I need 500 pounds of pressure there under the master cylinders, I have to push with about 100 pounds of pressure with my foot there. So that's easily enough done. This ratio, like, it's not quite exactly the same 400. That is close enough that I can do that. I can modify that with the bias bar in the brake pedal itself. There at that pivot point, it changes whether it goes more or less to the front or rear cylinders. So I'm happy with this, with a 0.875 diameter master cylinders, that I'll be able to stop the car easily enough. I can easily generate 100 pounds of pressure there. I mean, if I can stand on one foot and I weigh considerably more than 100 pounds, I can, I can generate 100 pounds easily there, which will be an appropriate force to stop the car. All right, folks, I hope some of you found that interesting or informative, or maybe even entertaining. I don't know. Anyway, thanks for stopping by. Give me a hand. Subscribe, like, comment. Oh, that's always it's always fun to read. So yeah, we'll see you next time. Thanks for stopping by.